Hello, I'm Vivek and I'll present our paper LEGOStore, a linearizable geo-distributed store combining erasure code, replication and erasure coding. Consider a web application that simultaneously serves users in the USA, where I am currently, and users in Australia, where many of you are in the conference. Such applications generally have some shared variables that they need to access, and they often rent data centers from a public cloud to store and access these variables. Typically, you don't just rent one data center, but take many data centers and replicate your data to ensure that the service is fault tolerant and available to the users. These systems have some common engineering trade-offs. First, it's important to maintain some form of consistency across these various copies. Second, good design is important to ensure that the latency is not too big. And third, when renting resources from the public cloud, we want to keep costs low. Erasure coding is an alternative to replication that can be cost-effective in many cases. In erasure coding, servers don't store entire copies of the data. Instead, they store code word symbols, which may be a partition of the data or a parity symbol. When an NK erasure code is used to store data over n servers, the original data can be recovered from any k of the n servers. Each server stores just a fraction of 1 by k of the data instead of a full copy. And this can reduce the redundancy overheads compared with replication. Erasure coding is widely used in data storage practice. Its benefits and trade-offs have been well understood, especially in the context of archival data storage and when the data is stored within a data center. Our focus here is on consistent, that is not archival data storage. And we store data not just within a data center, but in a geo-distributed manner. We aim to understand whether erasure coding can save costs at all, and if so, how we should design such systems. For this, we designed LEGOStore, a data store that offers linearizable consistency. Linearizable consistency, also known as strong consistency. It allows clients to access data via gets and puts. We aim to support high concurrency and non-blocking operations to the same key. Note that this precludes consensus-based solutions such as Paxos. Our design goal is to meet latency objectives and minimize overall costs. To bring out the full potential of erasure coding, we make a simplifying assumption that certain workload properties and system properties are predictable and aim to design high-performance solutions with the knowledge of these properties. LEGOStore employs 3 essential design ideas, the first of which is linearizable non-blocking protocols. LEGOStore uses an algorithm called ABD. ABD is a classical algorithm that provides linearizable get-put interface to the clients and fault tolerance via replication. ABD uses quorums and logical timestamps to ensure consistency. A quorum is just a collection of subsets of servers that have an intersection, for example, a majority. And any quorum set can be used to access the data. ABD has a put protocol that operates in 2 phases and a get protocol that also operates in 2 phases. For erasure coding, we use an algorithm called CAS, coded atomic storage. In CAS, the quorums are larger since they have to intersect not just at one node, but at k nodes. This is to ensure that get operations can properly decode the data. Like ABD, it has a 2-phase get, but its put operates in 3 phases. The additional phase is required in puts to make erasure coding work, and for reasons that are explained in the paper. This table has a comparison between ABD and CAS. In the table, we see that both networking and storage costs are inversely proportional to K. This table also suggests that CAS has bigger latency because of the additional round for the put, and CAS also has bigger latency potentially because it needs to access larger quorums. The interesting question here is how these cost comparisons and insights translate to the geo-distributed setting in the public cloud. It turns out that in practice, the analysis is much more nuanced and not as clear-cut as presented in this table. To understand why this is, let's just see the network pricing information in this table. Right? If you look at the highlighted boxes here, you can see that there can be 2 to 7 times difference in terms of cost, depending on which pair of data centers are talking to each other. Here is a table with pairwise latency information for the same system, and you see something similar. There's a lot of variation with latencies, and they can range from a few tens of milliseconds to a few hundreds. Thus, the first order analysis of latency and cost that I presented earlier are too simplistic to understand real systems. To understand performance and choose the best schemes, LEGOStore uses an optimization framework. I'll just give you a glimpse of the framework here. We assume predictability in workloads and solve one instance of the optimization per epoch. An epoch is a period of time where a given key's workload properties and corresponding system properties are relatively stable. The optimization framework takes as input workload features, pricing information, and network latency information, and aims to minimize an objective, which is the total cost. The cost includes compute costs in terms of VMs that are procured, storage costs, and networking costs. In particular, the optimization aims to find a cost minimal configuration, where by configuration, I mean whether you choose ABD or CAS, what the replication factor should be, which DCs are chosen, etc. The constraints for the optimization are tail latency constraints, consistency requirements, and the desired target availability. Here I summarize some key results and findings. We consider a setting with 9 data centers over Google Public Cloud. By varying workload features, we generated over 500 workloads and compared against baselines that are designed to represent state of the art. We found cost savings for workloads that range from 5 to 60%, depending on the workload characteristics. For nearly half the workloads we chose, erasure coding was the cost optimal solution. And the cost savings actually come from having significantly lower network traffic with coding. We found some counterintuitive insights pertaining to performance. The first is that there is no simple formula to determine the configuration, things like quorum sizes, based on the workload parameters. The relationship of the optimal configuration to the workload characteristic can be quite nuanced. Here's a picture. The x-axis represents the spatial distribution of workloads, and the y-axis is latency. Here, the 1 or 2 locations carry a majority of the load, shown on the x-axis. Depending on the target latency, the optimizer chooses ABD or CAS and the corresponding parameters. One interesting finding is that there's an intricate dependence of the configuration choice on the ratio of gets and puts, and this is due to asymmetry in the cost between get and put protocols. Also, interestingly, sometimes even CAS k equals 1 is chosen, which is essentially replication, but CAS is chosen over ABD, and this is due to structural differences in these protocols that lead to cost differences. Another surprising finding is that the highest value of K is not always optimal. This is because on increasing K, network and storage costs decrease as expected, but compute costs increase. Basically, with increasing K, quorum sizes become larger, and so traffic at the DCs increase, and you need more compute power to handle this. Our paper has a nice model for this, and we explore the relation between the best value of K and things like arrival rates and object sizes. Finally, we find that erasure coding does not always incur a latency penalty over replication. This is because in quorum-based protocols, the farthest data center is what dictates the tail latency. If there are multiple data centers at a similar latency, we can expand quorum sizes without incurring a big latency penalty. The optimization framework assumes an epoch of static workload properties. If a workload or system properties change, for example, if a data center fails, LEGOStore adapts to these changes by initiating a new epoch. Then a new optimization instance is solved. And if the best configuration is different from the current configuration, we perform a reconfiguration. LEGOStore has a new reconfiguration algorithm And this algorithm is handcrafted to couple well with ABD and CAS. Its goal is to minimize impact on client performance during reconfiguration. For our algorithm, the latency penalty of ongoing operations that are concurrent with the reconfiguration is of the order of 2 round trip times between a controller that issues the reconfiguration and the servers in the configuration. Another nice feature is that reconfiguration is performed immediately on being triggered in our algorithm. That is, there is no need to wait for ongoing operations to finish in order to move to the new configuration. This fast transition is enabled by some distributed algorithm tricks and a corresponding proof that ensures that linearizability is maintained. This is unlike several state-of-the-art approaches where you transition to the new configurations only after concurrent operations finish. Here is a sample trace of 10 minutes. 2 reconfigurations occur in this trace. The first is at 200 seconds due to an increase in arrival rate. Here you transition from CAS 5.3 to 3-way replication via ABD. Then at 400 seconds into the trace, a data center fails and another reconfiguration is triggered. This trace plots latency of put operations for two data centers that we chose. The reconfiguration itself happens very quickly. It happens within less than a second of, it completes within less than a second of being triggered. A small fraction of concurrent operations are slowed down, around a 500 millisecond penalty here. In our implementation, some operations are slowed, not during reconfiguration, but after moving to the new configuration. This is because some clients do not have the latest configuration information and have to burn a round trip time to acquire this information. So to conclude, we have studied the efficacy of erasure coding in linearizable geo-distributed data stores. Our work is on the heels of an emerging research area. In particular, I want to point out Giza and Pando, which study a similar setting. They made interesting modifications to Paxos and RS Paxos to ensure good performance in geo-distributed settings. Our work is complementary to these works as we took a deep dive into understanding what workload and other properties favor erasure coding over replication. Because they use Paxos, they cannot support concurrent non-blocking operations, but they support more complex primitives than simple gets and puts. An area of future work is to understand how our insights and analysis translate to consensus-based solutions. With this, I conclude my talk, and the code is available on GitHub.